In the last video, we looked at Lewis structures and how to draw Lewis structures with single bonds and multiple bonds. Now we're going to look at what's called resonance, which deals with Lewis structures, and then a couple of exceptions to normal Lewis structures. So let's start off here with what's called a resonance structure. Resonance structures are just when you are using a combination of atoms that has more than one possible correct structure. So this is always a good thing for people because they're glad that they can have more than one right answer, okay? But the key thing about this is that only the position of the electrons change, not the position of the atoms. So we're not changing how they're hooked together. We're just changing where the electrons are located. And in order to have a resonance structure, you have to have both a double bond at least and a single bond, or triple and a double. You cannot have all double bonds, really. You can't have all single bonds. It's not going to work. Okay. So what we have here are three different resonance structures on the left. Okay. And the one on the right is actually what the molecule looks like. It's kind of a combination of the three. So what we notice in these three resonance structures on the left is that on the top one, the double bond's in the lower left. In the bottom one, the double bond's in the upper top. And in the lower right, the double bond is in the lower right for the oxygen. So notice how the oxygen didn't change how they were arranged. This double bond just moved. And what we end up with is the actual molecule, and we draw it kind of with a dotted line, meaning that each one of these bonds between the N and the O is actually about like 1 1/3 bonds. Here we have a double, single, single, so it averages out to actually be about 1 1/3. What I'll have you do normally is draw these three resonance structures and not the actual average, but you will see the actual average one sometimes in like a textbook or something like that. So let's go ahead and draw the Lewis resonance structure for the following ion. Okay, we've got NO2 minus. So remember, we have to figure out all of our valence electrons. N has 5, O has 6. There's 2 of them, and this negative means that I have to add one more electron. So we're looking here at a total of 18 electrons. Okay, it's NO2. N's going to go in the middle. O's around the outside. We connect them. Now we see what we've got. Okay, everything has to have an 8. So if I would get everything lone pairs, that's going to be more than what I have available to bond with. Because I'd have 8 here, and then I would have 10, 12, 14, 16, 18. I would need 2 more, and that's not going to work. So what actually happens is that we get rid of one of those, and we make it a double bond instead. So here's one possible Lewis structure, but I can also have, when we do a double-sided arrow here, a resonance structure with a double bond on the other side. So same thing, just bonded to it, the different oxygen. And these would be our 2 possible Lewis structures, or resonance structures, for NO2 minus. Now let's look at some exceptions to our octet rule. And remember, the octet rule is that we need to have 8 electrons around everything except for hydrogen or helium, which are happy only with 2. But there are some that don't obey this rule other than hydrogen and helium. First one's a very odd one, okay, in the sense that it is an odd number of valence electrons. Plus, it's just not very common, all right? So what these are is that you have some, okay, we have a small group of molecules that have an odd number of valence electrons. I'm going to look at an example. I'm really not going to give you one of these to draw, but you do have to be aware that they are out there. So we look at this example here. Okay, we have NO2, but notice how there's not a minus this time like we saw in the previous problem. So what we end up with is 17 total electrons out of 18, and our N ends up having 7 instead of 8, and it's just fine with that. It's kind of just one of those weird occurrences, okay? An odd number of valence electrons. A way more common exception is what's called a sub-octet. Okay, think sub-octet. These are ones that are stable with less than 8 electrons around them. Think sub, less than, okay? The probably most common example is boron, okay? Boron is very happy with 6 electrons around it because it originally had 3 valence electrons. Okay, if I look at boron, it's in group 13, so it's going to have 3 dots. And so it's very happy just to share and get electrons from 3 other things. And now it's got 6, okay? Like it does right down here in the picture of BH3. So boron can have 8 if it takes an entire lone pair from something else. All right, now we're going to look at the other exception, and probably more common exception, and that would be an expanded octet. Expanded octets are where you can have more than 8 electrons around your center atom. Okay, but in order to do this, you have to have an element that is in the 3rd period or higher, and that means higher in number. Okay, which is actually 3rd row in the periodic table and down. Okay, because periodic table goes 1, 2, 3, 4, 5, 6, 7. So the 3rd row and down or higher in number, because these guys all have d orbitals that they can use for the extra electrons. These extra electrons can be in the form of a lone pair, okay, or a double bond. Okay, so any way that these atoms can have extra electrons around them. So we'll see here with phosphorus, okay, has an expanded octet. It has 5 chlorines around it for a total of 10 electrons, all in a bond. I could also put extra electrons as a lone pair. I could also put extra electrons as a double bond. It just depends on how many electrons you have available to bond when you draw a structure. So let's look at a couple of examples. Okay, we start off with XeF4. Okay, xenon is actually a noble gas, but it's low enough on the table that it'll actually bond. So it's going to have 8. Fluorine has 7, and there are 4 of them. So we start with xenon in the middle. We do Xe, and we connect it to all 4 Fs. Okay, each F is going to need its 8 electrons, so we're going to go ahead and put all of those around and see what our number is. Okay, so we've got 8, 16, 24, 32, so I'm still 4 short. So where are those 4 going to go? Well, they go right as lone pairs right to xenon. Now why can't I do a double bond to fluorine and give fluorine 10? Because fluorine's only in the 2nd period, so fluorine's never going to double bond in the sense to have more than 8 electrons. It only ever has 8. Okay, so let's try the next one, ClF3. Cl and F are both in the same row, Cl and F are both in the same group, so they're both going to have 7. So we've got 7 times 4, which is 28. I'm going to go with Cl in the middle, 3 Fs around. Okay, I'm going to give everything 8 again. And 8 here, and let's count. 8, 16, 24, 26, 28. The extra lone pair again has to go to chlorine. So why don't you go ahead and try the last 2 there. And this is what you should get for the last 2. Okay, now look at our last few questions. So summarize the exceptions to the octet rule by comparing these formulas and phrases. We have PCl5, ClO2, BH3. One of them is going to be an expanded octet. Okay, one of them is going to be an odd number. And one of them is going to be less, or a sub-octet. So one of these three should be very easy to pick out, and that should be our sub-octet because I gave you this example in the notes. Okay, if you don't know, add all the electron numbers up. Okay, well if I start with PCl5, P is 5, Cl each has 7, and there are 5 of them, so that would be a total of 40. Well, that's not an odd number. Probably not going to be less than that. ClO2, oxygen is 6 times 2, which is 12. Fluorines are 7. 12 plus 7, well, that's 19. So that one has to be our odd number, because 19 is an odd number. BH3, each H is 1, so that's 3 borings in that group that has. There are 3 H's, each one's 1, that's 3. Boron is 3, a total of 6. Notice how I said boron is 3, so that is our less than, which means then the expanded is PCl5. If you don't know, draw them out. Let's look at the last question. A classmate states that the binary compound having only single bonds displays resonance. Is this true? Why or why not? Binary compound meaning two things, so A and B, they have only single bonds and it displays resonance. That is totally false. Okay? Even if you had two B's, okay, it's still going to be a binary because there's still two things. The only single bonds part kills you. You need to have a place where the electrons can move. So I need to have at least a double bond and a single bond, or triple and a double, or triple and a single. You cannot have just single bonds. There's nowhere for the electrons to move.